the interface of Grasshopper, a couple of as well as a couple of methods for modeling, kind of variation with a modular tile or modular geometry. So the first thing to do is to open up Grasshopper. If you have Rhino 6 already installed, so just type in Grasshopper in the command line and press enter. And here we are. This is the Grasshopper canvas. The first thing I'm going to do, and I'll just make some notes of the interface as I go, but the first thing I want to do is reference some geometry that I have in Rhino into Grasshopper. And the way that I do that typically is going to be under the Parameters tab here and under Geometry. And so these components all represent a few simple geometric types. Actually, every geometric type that you can use in either Grasshopper or Rhino. And so in order to reference a surface, what I want to do is go to this component that says and you can see, first of all, so I've just placed it on the canvas here, the kind of two-dimensional workspace. And by default, I'll hover my mouse over the little error bubble, or the error message there. You can see that my component is creating an error, which I can tell because it's yellow. And if I hover over that error bubble, it says floating parameter surf failed to collect data. And what that means is there's no kind of information inside of this. And so these are what are called these kind of parameters. They just kind of hold information. But like I said before, that's what allows us to reference Rhino geometry into Grasshopper. So going over into my Grasshopper viewport, I'm going to click on the little surface creation, and I'll make a vertical plane here in the viewport. And I'm not worried too much about scale now, so that. And then to reference geometry into Grasshopper, I'll just select my component, right-click on it, and I have two options: set one surface, which I'm doing right now because I just have one. But if I had multiple, I could also hit set multiple. I'll just click that one, click on it. There you go. So now my component is turned to gray, light gray, and if I select it, it turns to green. And you'll see that whatever I do to my surface in Rhino, those changes will be reflected. So this is linking now my Grasshopper script to the geometry. Okay, so now what we need to do is kind of explore, the first thing I'm going to do is explore just a basic method of modifying this surface. But just to give you a point of reference, what we're going to do is use this surface as a kind of base to populate a module onto. So what I want to do now, basically I'm going to modify the geometry of this surface by subdividing it, moving the points relative to an attractor, and then rebuilding that surface. First thing I need to do is subdivide the surface into points. So I'll go in Grasshopper over to the Surface tab, and I believe under, let's see, Utility, there's a component called Divide Surface, the first one there, and I'll place that on the canvas. Now, I'm just going to do a couple of things quickly here to kind of give you a point of reference, how stuff works. You don't need to do this part, but I'm going to draw a curve really quick, just doing here. And I'm also going to So the way that Grasshopper works is it uses what's called a parameter space. With a curve, for example, and I can plug in this little component called evaluate, plug my curves into a little component called evaluate. And what that does for me is it allows me to gain information about that curve based on a specified parameter. So by the way, every time I hover over an input or an output of a component in Grasshopper, it'll tell me, what's nice about Grasshopper is it tells me what kind of information it wants. So for example, with my evaluate surface, if I hover over my S input, you can see that it says surface, and you can also see there's a little icon there. And if you remember, those icons are the same icons that we see under parameters under geometry. And so that icon tells me that this input requires a surface and not a number or a curve or some other type of information. So if I plug in my surface there, it should be able to use that. Now, the other thing that these two components are both asking for is something called a parameter value. So you can see on my curve evaluation, it's asking me for a parameter t, and the little symbol is indicating that that needs to be a number. Now, while I'm here, this is actually not under geometry. Geometry under primitive. There are two types of numbers in Grasshopper. There's what's called an integer, which, if you remember, it's just a whole number. And then what Grasshopper just calls a number, and that will allow you to decimal. So if I go ahead and get a number slider, and I'll go to my input section under parameters and go to number slider, I can just place that guy on the canvas. And then if I were to plug that into my T, you can see, first of all, that it's turned to gray. And you can also see that some new stuff has showed up in my viewport in Rhino. Now, first of all, if I drag this number slider around, you'll see that those points are actually moving. So as I stated before, this allows me to collect information about a curve at a given parameter. So for example, it's giving me the point on the curve. It's giving me a tangent vector, which means the direction of the curvature at that point. And then it's giving me the angle, so similarly, direction. So what I want to do is be able to evaluate any point along that whole curve. Now, by default, this kind of what's called parameter space is defined by the length of the curve. So for example, I can also use a component called length. This one is specifically for curves, so curve length. And then if I go to input and panel, and a panel is just a little like text box that allows me to see like a list in a visual way. So I can hover over the output there, and it's telling me the length of those two curves. And if I plug that into my panel, you can see that one of my curves is 27.03 inches long, and the other one's 49 inches long. So if I plug those directly into my T, you would see that the point would go roughly to the end of the curve. So sometimes it's different when you have curves that aren't straight. But the point is, if we wanted to evaluate a point along that curve that was, say, halfway the distance, instead of using the length of the curve and dividing it by 2, because as we can see, that's a little bit imprecise, we can also use a method that's called reparameterize. So on the C input, the curve input, if I right-click on that input, I have a few different options here to kind of modify the data as it's coming into the component. And one of those options is reparameterize. Now you can see that the point along that curve moved. So what reparameterize does is it alters the parameter space of an object to between 0 and 1. Now when I move my slider, you can see 0 is the start of the curve, 1 is the end of the curve, and if I were to enter 0.5, that would be the center of the curve, 0.25 would be 1/4, etc., etc. Now, the other thing I want to quickly mention here is parameter space is not evenly distributed. So like curves in Rhino are drawn using control points, and you can see that those are basically what define the curvature. So the same is true for a line, a curve that has no curvature, essentially. But if we were to move these control points, straight line, 2 points that are kind of halfway in there, can see that now, although my parameter is set to 0.5, the point is not exactly centered along the length of that curve. And the reason for that is it's actually distributed according to the weights of these control points. So now it's halfway in between the weighted control. Same would be true if I started to kind of bunch up all my controls for this guy. Once again, you can see that that point is not probably halfway along the length of the curve, but it's halfway according to the parameter space of the control points. And I'll explain later why that's. But just so you know, parameter space is not the same as length usually, not always. So now that we understand what parameter space is, I'm going to apply the same principle to my surface. So like I did before, I'm going to get what's called an MD slider, or a multi-dimensional slider. And this is just like a kind of similar to a one-dimensional slider, except that I have a kind of X and a Y value are coming out. Get a panel here. It's giving me an XY, like a coordinate. So if I plug that guy into my UV, which is the same as the T on my curve, it's going to deliver or return for me a point, so an XYZ coordinate, or a point, a normal vector, which just means the direction perpendicular to the surface at the given point. It's going to give me U and a V vector, so along the directions of the curve, or sorry, along the directions along the surface. And it's going to give me a frame, or what's a kind of miniature like plane, so a specific kind of coordinate space relative to that point. And just like I did before, if I reparameterize the surface, I'm just right-clicking on the surface input, clicking reparameterize. Now you can see I can change the location of that point on the surface based on where I position my MD slider. And so just like before with our curve has a start and an end and a single path, right? So our curve only requires one parameter to find any position along that point. But because of the nature of how surfaces work in Rhino, we actually need like two numbers to find any possible location along our surface. That's what's called a UV parameter, or a UV direction. It's like a kind of miniature coordinate space, or XY space, that's just local or kind of specific to that surface. Now we can get back to the actual task at hand, which is subdividing our surface. So if we get back to this component that we created earlier called the surface divide, again, that can be found under surface, under utility, and this component divide surface. And again, I'm just going to look at the inputs it's asking me for. So the first one, the S input, is a surface. That U component asking me for a number, and in this case, you can see our little icon is telling us that what we actually want is not a number with decimals, but an integer, so a whole number, right? Because you can only divide it into whole different points. And the same for our V. So again, every surface has a U direction, right? Up, down, and every surface has a V direction. We can find points along the surface by interpolating a U and a V. So this is asking how many times we want to subdivide two directions, or in each direction. And so like before, I'm going to just make a number slider stuff. And so just so you know, the other way you can get components in Grasshopper is if you just double click anywhere on the canvas, it'll bring up a little search box, and I can type in a number. Or I can type in, the name of a component, for example. I could type divide, and it would show me a whole bunch of different components that I have that have the word divide in the type. Now, one of the quick ways to make numbers, of course, is the number slider. Let's say we don't want to start with the default values, but we want to start with a specific number. I can just type in the number and Grasshopper and press enter. Grasshopper will automatically create a number slider with that number. I'll plug that into the U. Let's say I wanted to divide by 15 in the V direction. I'll just type in 15. Now, in order to edit sliders, so first of all, obviously I can move the slider, but you can see that this one only goes from 0 to 10. If I wanted to change the range of that slider, I just double click the darker gray portion of it. And then in here, I can double click and type a different number, so 20, or I can drag the decimal points to range. That's the minimum and maximum range. You can also change it to, like I mentioned before, you can have numbers with decimal points, integers, or even and odd numbers. Leave it on integers here. And we can correction. Okay. So that's pretty simple. We've just created, again, a number of points that are on our surface. And what we're going to do now is we're going to move those points around parametrically. So what I'm going to do first is get another generic geometry component. So under parameters, geometry, I'm just going to get this first one called point. And when I right click on point and go to set multiple points, because I want to use more than one attractor point, I have a couple options. So first of all, up here in my regular command line, you can see if I tap the option there, I can link them to a point, I can snap to a point along a curve, or I can use what's called a coordinate. And the coordinate, which is only really works for the point component as far as I know, just allows me to click in my Rhino viewport and place points that way. And then, so these aren't actually in Rhino. They're not linked to a physical point that's in Rhino. They're just kind of inside of this component. So now if I select this component, as you can see, I also have the option to move these guys around, to use their own like kind of individual little gumballs, kind of move those points around. That. So now I have 4 points that are located kind of randomly around my surface. I'm actually also going to hide my surface at this point. Good. Okay. And what I want to do next is modify the location of all these points based on their individual proximity to my attractor point. And I can do that if I go to Vector tab, Vector. Here we go. So under point, we can use this component called closest point. And I'll place that on the canvas. So these are all our points on our surface. So if we hover over the inputs on our closest point, it'll say point to search from, and it'll say cloud of points to search. And then if we hover over the output, it'll say point in C closest to P. In other words, if we plug in our attractors in C and we plug our surface points in P, it'll tell us for each one of those points on the surface which one of these attractor points is closest to it. And it'll not only tell us that, it'll also tell us the distance between each point on the surface, which is the information that we really want out of it. So if I look at the D output, you can see it says distance there, and it's telling me that that's a number. That's a kind of a range of different values. And so what I can do with that is I can use that to modify or to drive how I start to move the points that define the surface. Now, what I want to do next is define how my points are going to move. So now we figured out, based on the proximity, we can drive how far they'll move, but we also have to create a way for them to. The way that we're going to do this is using a vector. So if I go under the transform component, you can see we have a lot of the same types of transformation that Rhino itself uses. We have mirror, we have move, we have orient, rotate, rotate 3D, etc. They all require different information, and they all kind of transform geometry different ways. And we're just going to use the move component. And if I place that guy on the canvas and look at the inputs, you can see it requires a geometry. So any type of geometry, points, surfaces, curves, etc. And it requires a translation vector. So for those of you who remember from your math, a vector is a direction and a length. So if we go back to the vector component here, and we go under the vector, you can see there's a whole bunch of ways that we can create vectors. We can create them using an X, Y, and Z component numbers, like X, Y, and Z values. We can create them using the kind of generic world X and Y direction and Z direction. And we can also kind of compute and modify vectors in a number of ways. Now, from before, when we actually subdivided our surface, we also got our normal vectors at each one of those division points. And again, the normal vector for a surface is the direction perpendicular to that surface. Now, there's a couple ways we can kind of modify here. What I'm going to do first of all is I'm going to just utilize this normal vector, and then we'll make a vector in another way, so you guys get a sense of the difference between doing it in different ways. So our normal vector is already exists, right? And if I go to panels here and plug my normal vectors in, you can see because we have a flat surface there, our normal vectors are 0, -1, and 0. So that means our x direction, which is this direction right now, 0. It's -1 in the y direction, so our surface is pointing that direction at every point, and then 0 for z as well, because it's surface. Okay, and what we need to do then is just modify the length of each of those vectors based on the distance of each point from its attractor point. So the next thing I'll go is vector. And again, under vector, I believe I'm going to get this component called amplitude. So we already have the direction established. What we need to do here is we'll plug our normal vector into the vector on our amplitude. And then we need to use this distance factor to change the length of each vector. So right now, those distance factors are based literally on the distance between each point and closest attractor. What I want to do is modify that range to be the inverse. In other words, the points that are closest to their attractor, I want to move the most, and the points that are furthest from the attractor, I want to move the least. In other words, I need to kind of invert the range in a sense. The easiest, there's a lot of ways you can do that using math, but the easiest way for us is going to be use something called the remap values component. If I double click on the canvas here and I just type remap, you can see it gives me that that range and or that component, I'm sorry. And then if I go to sets over here, or I'm sorry, maths, and I can go to this section called the domain. So what this component will do is it will take a range of numbers and it will remap them based on, or it'll take a whole set of numbers and it'll remap them based on a start range and an ending range. And a range literally just means a start and an end value. And in Grasshopper, those ranges are called domains. And so under this domain component, we have a domain or a component called construct domain. And that component, you can see here, allows us to enter start value and an end value, and then it kind of composes that into a range or a kind of type of data that can specify a range. So once again, we can utilize this, and I'll plug that in. So let me do this component quickly. Again, it wants a number of values. Those are actually our distance values, distance of each point to its closest attractor. It wants a number of, it wants to know the range of the existing the existing range, I'm sorry, of the set of numbers. Again, I'll go to parameters, see that these are just distance values. You can see we have a whole bunch of different numbers and they range from between like 9 and 14 or 13. And so what we want is to tell it what the existing range of our set of numbers is, and it'll take that and kind of remap proportionally to our new range. So for example, and I'll do this really quick here. If I make a range that's 0 to 5, you don't have to follow along with this part, I'm just works. If I make a range from 0 to 5, and then I make a number slider from 0 to 5, that's the existing range of a list. That's the starting range. And then I could copy, so I'm just using Control C and Control V. And also, like you do in Rhino, you can like tap Alt on the keyboard while you're dragging something, and that'll copy it as well. And then I'll remap that, or I'll make a new domain for my target domain, and I'll remap it from 0 to 50. And then I'll copy this range, or this panel, to look at the output. So once again, you can see it takes every number, says, okay, 0 from a range between 0 and 5 is the lowest, and then it remaps it to the lowest value in our target domain. For example, if I set this to 20, you can see it's now remapping those numbers proportionally from between 0 or from between 20 and 50. 100, likewise, it's going from 20. So it just takes an existing set of numbers based on a range and puts them in a new range. So working with that principle, I can remap the existing set of numbers of my domain, or my distances. And what I'm also going to do now is get a component called bounds. What this guy does is it takes a list of numbers and it spits out a domain. So it tells me what the range is of the numbers that I have in an existing. So it's telling me right now I have a bunch of different ranges. Now, I'm not going to focus on this too much because this kind of gets into data organization. But just to kind of touch on it quickly, you can see right now what's happening when I look at the wires that connect different components. There's a solid wire and there's a dashed wire. There's also this kind of double line wire. So that actually gives me some information about the type of about what the data is that's kind of moving between components. So a single line means that there's one value in a list. See, that's just our surface. A double line means there's more than one value. So that's our list of points that has 4. And a dashed line actually means we have what's called a grafted list, or a list tree, a list with multiple branches. In essence, it's a list of lists, right? You can see that like before, we had one list with a single kind of gray line and then a value at the top. Now we have a whole bunch of different lists that have their own gray line and they have their own number. And basically what that means is it's kind of structuring the data so that we have like separate lists within a single list. So that allows us to kind of do more complicated calculations and stuff. Now, this isn't relevant to what we're doing, so I just want you to be aware that there are sort of like what's called a flattened list, or a list with a single branch, and what's called a grafted list, or a list with multiple branches. And for us right now, what we're going to do is just flatten everything because we don't really care. We don't need to have this information in separate lists. And I can do that by right-clicking on the output. And you can see I have a dashed line here, which means I have a grafted list. I'll right-click on the output. You can see that's what these two little buttons do. And if I hit flatten, now you can see I have a double line. And if I plug that into my component, we now have a list with only one branch, or only one kind of sublist, which is just fine for what we're doing. And I will do the same for my normal vectors. because kind of screwy things start to happen when I combine lists with different kind of organizations. In other words, flattened list and grafted lists. So I'm going to right click on the normal vector and also go to flatten. And so I don't know if you remember, but before when we were getting the bounds of our distances, it was giving us a whole bunch of different ranges. And those were for each of the individual sublists. And now it's just giving us one, which is great. So it's giving us a minimum and maximum set of distances for the whole surface, for every single point. So I'm going to plug that into my start domain on my remap component. And then I'll keep this guy. Actually, I'll keep the other guy because I'm that far. Okay. And so now that's our existing list. You can see we have a bunch of numbers kind of between 9 and 15, like we mentioned. And now you can see those numbers are all a lot smaller. And if I compare them to their kind of corresponding numbers from before and after, you can see we have the smaller numbers are smaller and the bigger numbers are bigger. And so, like I mentioned, we want to actually have the distances that are closer move more. So what I will do, well, let me just plug this in. I'll change that in a second. But now we have our remapped numbers. So I'll plug that into my amplitude here. Again, that was just a number for that sets the new length of our normal vectors. And then the things that we're trying to move are the points themselves. So I'll plug again on my surface divide, those are my points. Plug those into geometry. And now they're moving by a default vector, which is already in this component. Just replace that vector with my amplitude vector. See, I now have a bunch of moved points in Rhino. And if so, the other thing that I should mention about the interface here is that all components can be like previewed and unpreviewed. So as we kind of go along and add more information or additional components, we're actually also like kind of duplicating in a sense that information. So these points all still exist on that surface. This is kind of how it becomes parametric, right? Because every change is sort of set up in a formula so that we can alter what things are doing, right? So if we change the number of subdivide our surface has, it will change the points that are moving. And if we modify our attractor points, it'll also change how far individual points are moving, so on and so forth. So what we want to do is actually unpreview the stuff from before that we actually don't need to see because it's just starting to get messy and hard to understand. So each component I can right click on and I can toggle the little preview button. Now you can see those points that were on the original surface disappeared. Again, we can just toggle them back on if we want to see them again. And I can also select multiple things at once by just clicking and dragging or holding Shift, like I would just selecting things in the Rhino viewport, and right click on the canvas, toggle everything on or off, preview on. Now we're just seeing those points from our subdivide. And let me amp up the range here. So now you can see the points that are furthest away from our attractors are the ones that are moving the most. And again, we want that to kind of be the opposite. We want to move points that are closest to our attractors the most. And so in order to do that, rather than sorting it by a low start number and a high end number, I'm just going to switch these. I'll plug the 8 into A, and I'll plug the 0 into B. Now, in case you guys don't know this yet either, in Grasshopper, you can plug things in, obviously, by dragging them and plugging them in. You can also hold Control as you're plugging in, or as you're dragging a wire. You can see a little red cursor shows up, and I can unplug stuff. And I can also hold Shift, and I can plug multiple things in. You can see that's going to start to cause errors, but I can plug as many things as I want into a single input. You can also right-click on an input or an output, go to disconnect, and disconnect individual wires, or hit disconnect all. So you're aware of kind of how you can modify the way you're plugging things together. Okay, and so now you can see we kind of have a surface that's a little bit more doing what we want. And again, we can modify any of our attractor points, and we can make the geometry change based on which one is closer and like where it is in space. Which is all well and good, but we still just have a bunch of points floating in space. What we actually need to do now is reconstruct a surface. Delete these to get them out of the way. So I will go to surface component. I think it's under primitive. Oh, it must be under freeform. And this top right component called surface from points. What this guy does, like it says, is it requires a bunch of points. And it will basically interpolate a surface, or it actually requires a grid of points, not just a bunch of points. They have to be an even number in each the u and the v direction. But it requires a grid of points. Those are our points, and it requires a number, or in other words, the number of points in the u direction, just so it knows how to interpret the points. And so the way I can tell how many points I have in the u direction is I can go all the way back here where I plugged in how many subdivisions I want in the u direction of my original surface. And you can see that I have 17 subdivisions, but and let me just use this curve again to visualize what I'm going to talk about next. So in Rhino, I can also take a curve and I can type in divide. And let's say, for example, I divide it into 3 segments. So I'll press enter, and it'll create points evenly spaced that generate 3 individual segments. But you can see that because I divided it into 3 segments, I actually also created 4 points. So 1, 2, 3, 4. And the same is true when we subdivide a surface. So even though we subdivide the surface into 14 equal segments, or I'm sorry, 17 equal segments in one direction, we're actually making 18 points in that same direction. So that's all to say that we can't actually quite plug this 17 into the U. You can see that that causes an error. So again, yellow and red means that something's wrong. Usually yellow means you don't have enough information yet for the component to work. Red means that you're actually doing something wrong. Things are failing. So if I look at the error value there, it says the U count value is not valid for this amount of points. So it's trying to take that 17 and generate a surface. Can't figure it out, basically. So in other words, we need to add 1 to this number in order for this surface component, to be able to make the surface. And if we go to the Math tab, go to Operations, you can see we have a whole bunch of kind of generic mathematical operations. We can also write our own formulas, which is called evaluating under here. Not sure where it is, but you can also just double click and type evaluate. That allows us to kind of write our own expression or our own mathematical function in here. But because ours is just a simple addition, we're just going to component add or addition. I'll add this number 17, and then I'll make a number 1 with a slider, and you can see the output is now 18. If I plug that into the U, now our component turned gray, and we now have a new surface, Rhino. And so if I select these and preview them, now we're just looking at what that surface is creating. And again, these numbers back here are really just going to kind of define like a resolution. So we don't want a ton of numbers here. We really just need enough for this surface to be clear. At some point when I turn them up, it doesn't really make a difference in terms of how good that surface looks. But if I turn them way down, you'll start to see lower. We're losing kind of some resolution there. So we don't need a ton of values. Computer runs slow. But we need enough that we really get a kind of clear transformation based on our attractor. Now, the other thing I want to address here is you can see we have 3 points on one side of our surface, and we have a point on the other side of our surface. But it's just measuring the proximity to each of those points, and it's always moving in the same direction. So like we did before when we talked about those normal vectors, and let me get a visualization component here. So there's a component called vector display, and that'll just allow me to kind of see a vector within the viewport. There are points, and those are our normal vectors. And let me turn the surface. Now you can see I have a little arrow at each one of my points, and that's showing me the direction. So basically all we did was we moved each point in that direction based on a distance derived by how close it was to an attractor point. But because that direction is defined just by like what the surface is originally, it's all going to move in one direction. So even though this attractor point may be closer or further, and you can see it is affecting our surface geometry, it's not moving towards or away from that point. It's all just moving based on proximity. So to fix that, we need to create a different kind of vector. Rather than just using the generic surface normal values, we're going to make our own vectors. So I'm going to go to the vectors tab up here, go to vector, and go to vector 2 point. And so that will allow me to create a vector by choosing a start point and an end point, what it's calling a base point and a tip point. So, like with anything, we tell it where the vector starts and where it ends in kind of XYZ format. It should be able to give us a length and a direction. So in order to do that, what I'm actually going to do is first make a vector between every single point on my surface and its closest attractor. So back here where we did our closest point, see that one of our outputs was, again, the closest attractor point, each point in the surface. Closest point in C to every point in B. So if I plug that into B, now you can see everything working. And I'll also plug the vector into my visualize. So now we can actually visualize in the viewport. Visualize in the viewport which attractor point each surface point is being drawn towards, and we can visualize what direction it's now going to move rather than just perpendicular to that surface. So if I were to give you this, we'll move the attractors. So you can see as I move this guy out, fewer points are being attracted to it, and it's changing the direction that those points are going to move, the ones that are attracted. Just like that. Okay. So now I can simply replace the vector I was using before, which was my normal vector, with these new vectors I've drawn that set a specific direction relative to each attractor point. I'll plug those into my amplitude. Actually, real quick. Now if I plug those amplitudes, you can see that it's kind of moving, or it's changing the distance of each point, or the distance that each point moves based on how close it is. And once again, you can see that we're actually going to move past the point in some places, which we don't want to do. So we go. Okay. And the reason we don't want to do that, by the way, if I crank this way up, points will actually start, like the surface will start to turn inside out. Now that doesn't mean I can't make the surface that way. Turn it on. See what's happening is each point is turning inside out the surface. that's not really what we want, right? Starting to kind of pinch at those intersection points. So we could fix that by moving the control points out, or we could just turn down or move. And so again, this will affect our geometry, right? So if we want more difference in how the surface is moving, turn that up, and then we start to move the attractor points away. And you can see, based on the closeness of the attractor point, the kind of sharpness of the points that are drawn to it. Really, really sharp as it approaches the surface. Also kind of tune like not only how far it's moving, but like how the surface geometry is really. Okay, so that is a kind of brief introduction to Grasshopper, and will allow you to kind of modify a surface geometry. I'm going to go ahead and end this video, but there will be another video after this that explains how to populate a surface with a module, and then also how to vary a module rather than just kind of morph it. So that will be in a follow-up tutorial. Off now.